All right, I think we can probably get started. So welcome back. Today, our topics for discussion are closely related to one another. The first is the quark model, which started out as a way to try to organize the increasing multiplicity of subatomic particles that people discovered in the 40s and 50s. And deep inelastic scattering, which is a class of experiments which ended up providing the confirmation that this quark model corresponded to the underlying reality and that quarks were real particles. So how does this story happen? This is a typical plot that you might have seen from an experiment, say in the mid-1950s. So people start to pair the powerful accelerator, the synchrotron, along with the increasingly powerful detection techniques, both the bubble chamber, which is able to produce direct images of the interaction of particles with matter, as well as the new class of electronic detectors, starting from the spark chamber that we discussed last time, and moving on to more powerful techniques like the wire chamber, which we'll discuss in a future lecture. And you can see that the typical idea for these experiments is that you inject your beam onto a target. In the case of the bubble chamber, the target is also the detector. And then you basically count up all of the tracks coming out, you measure their curvature, and you make the mass of some final state, maybe a 3 pion final state or proton plus 2 pions, as is shown here. And then you make histograms of the invariant masses that you calculated, and you look for peaks in this distribution. And if the peak is, reaches a certain level of significance above the background, here indicated by this kind of drawn curve labeled phase space. So that's just sort of the continuum of events of the type that you would expect to emerge if there were no resonances. And then you see this big peak, in this case at 765 MeV, which stands well above the background. And this would be considered a good evidence for discovery of a new resonance. And then as these resonances are discovered, people start to calculate not just their mass, but also their width or their lifetime, and try to disentangle if they're the same resonance that's already been seen in a previous experiment or a new one. And the number of particles starts to explode. First, there's just a handful of resonances, and then there are dozens. And eventually, if you go and look in the PDG now, there are hundreds of mesons, which you can see. So there's a big flowering of these experiments at CERN, at Brookhaven, at Berkeley, all over the place, which are sort of filling up our PDG guide of resonances. And this is sort of causes a little bit of consternation among physicists of the time. Of course, it's great if like every PhD student can have their own resonance to study for their thesis. And it's kind of a nice program for experimenters in the sense that there's plenty to do, right? For each of these particles, you can make increasingly precise measurements of masses and lifetimes. You can try to infer what the quantum numbers of these things are by the decays that they do and don't have. But what's missing, at least circa the 1950s, what's missing is any kind of scheme for organizing this information. With every new resonance that is discovered, it becomes, I think, less and less plausible to physicists that these are truly fundamental particles. For one thing, there's just simply too many of them. Secondly, there appear to be certain regularities in the structure, certain structures which are repeated over and over within different families of particles. So you have this very typical distribution where there will be a neutrally charged sort of version of the particle, and then positive and negatively charged versions of the particle. They're masses and lifetimes are not identical, and sometimes the allowed or forbidden decays, for example, based on the charge, might mean that the phenomenology of how you see them in the detector is rather different, and yet they also somehow seem to belong to the same family. And then these family structures are repeated over and over again at higher masses, almost as though there's some kind of chemistry, an analog of chemistry going on, in the same way that you can move up the periodic table and form the same molecule using a heavier element that has the same valence electron structure. So too does it seem that somehow you can form heavier families of mesons or heavier families of baryons by perhaps moving up to some higher mass constituent that would play the role of the atoms in chemistry. In particular, we talked a couple lectures ago about the idea of the strange families of particles. So we have these sigma baryons, of which there is a neutral version, a positively charged version, and then a negatively charged version. These somehow seem to have some relation to the neutron and proton in terms of the structure of the masses, but introducing the strangeness and then moving even to a strangeness of -2. Remember, Gell-Mann proposed these rules that strangeness could be changed by 1 unit in decays which were mediated by the weak force, but only 1 unit at a time. So you're able to reckon that there's this new family of sigma baryons with strangeness -2, which decay via cascades through these guys here, and then eventually back to neutrons and protons, always just changing strangeness by 1 unit at each stage of the decay. And remember that these decays proceed slowly because there can only occur via the weak force. And so people started to draw pictures like this, Gell-Mann in particular, calling this the 8-fold way, because there's 8 different baryons on this chart. And once you can draw pictures like this, grouping together particles along multiple axes, you have this axis here, which is the electric charge, which is the same along these angled lines. And then you have this axis here, which is the strangeness, which is the same along these lines. And you can kind of see that there's particles taking up each space on this grid in a regular fashion. The reason why the number 8 is involved has something to do with, we now would say, has something to do with the number of underlying constituents, quarks, we now call them, which are making up each of these particles. These groupings are related to the SU3 symmetry of the standard model, which is only an approximate symmetry, since the masses and lifetimes inside a family are different. For example, the neutron has a lifetime, whereas the proton does not. They're nearly mass degenerate to within 10%, but not exactly the same. Nevertheless, this approximate symmetry that you see within the families is suggestive that there's some kind of physical principle underlying it. And that's one of the inspirations for this quark model. One can organize the mesons into similar groupings of 8 called octets. And this octet now has the strangeness 0 line running through the center. Those are the pions. And then we have kaons at strangeness of 1 and -1. For each of those, there's a Q equals 1 or -1 version and a Q equals 0 version. The fact that this picture that these can be grouped in the same kind of grouping, the same 8-fold grouping as the baryons on the previous slide, suggests that there's something the same about the underlying constituents, even though baryons tend to be significantly heavier than mesons, especially within the same family. So people's thoughts start to go to like maybe there's different number, to extend the chemistry analogy, maybe these mesons are lighter because they consist of fewer atoms, or what we would now say fewer quarks. One very suggestive grouping that was drawn around that time was the following one. So you have these baryons. There seems to be a family here with strangeness of 0. And you can run from a charge of -1 up to a charge of +2. Then for strangeness -1, you have a similar grouping, although here we don't have the doubly charged version. And then people discover these baryons with strangeness -2 here. And if you sort of draw this thing, it seems very suggestive that there should be a missing member of this kind of fraternity of particles here with strangeness of -3. So these are highly suggestive that there should be an undiscovered baryon here. And that is discovered eventually through a cascade decay of a experiment at BNL at Brookhaven. There's a synchrotron there called the Cosmotron. They named it the Cosmotron because their aspiration was to create an accelerator which could provide beams more as energetic as the higher energy cosmic rays that have been observed around the time. Kind of a cool name. So what you have here is a charged kaon beam coming in from the bottom of the picture. This produces a interaction vertex here. And at that vertex, in addition to some other stuff, there's a particle which will become known as the omega minus created here. That decays by emission of a charged pion to one of these sigma baryons. Then it decays down this chain of strangeness to a lambda, and finally to a proton. And so the interpretation here is that at each of these decay vertices, basically one unit change of strangeness is happening due to the weak decay of the omega minus. And so working backwards from the proton strangeness 0, this guy has strangeness 1, and we get all the way up to strangeness of 3 here for the omega minus. And so that prediction that there should be a particle with Q of -1 and S of -3 is borne out by the experiment. So this is a strong piece of evidence that this underlying picture, the eightfold way, these symmetries are physically meaningful because we can understand things well enough in order to make predictions of new states that haven't been discovered yet. Okay, but what is the underlying physics of what's going on here? So Gelman, and there's a guy named Zweig who's working around the same time who proposes an equivalent model. He calls his particles aces rather than quarks, but the idea is really exactly the same. And the idea is the following. So the quark model as proposed in 1964 claims that the underlying particles, the particles that explain the groupings on those eightfold way pictures are called quarks. Quarks can be bound together in groupings of either 2, in which case they form mesons, or of 3, in which case they form baryons. There must be some kind of confining force which prevents them from being directly observed. We don't see any evidence of the individual quarks, for example, in our bubble chamber photographs. So there must be a force which confines them to only exist inside of mesons or baryons. But the nature of that force, for now, is left unspecified. The mesons and the baryons, since they're both made of quarks, are now grouped together into a larger family called hadrons. In the original quark model, what's necessary to explain all the particles on the last few slides are just three flavors of quarks, which are given these sort of whimsical names, up and down, for the quarks that are found in the proton, neutron, and in the pions. And then the strange quark is responsible for giving strangeness to the particles that have this quantum number. So there's a concept sort of inherited from nuclear physics called isospin. This is the quantum number that, for example, distinguishes the proton from the neutron. And this isospin can now be understood as a quantum number, which represents the difference in the number of up and down quarks making up a hadron. And then this new quantum number strangeness, which has been proposed, represents a difference in the strangeness in the number of strange quarks inside of the hadron. So all of this is like a bit fanciful, and especially this observation that the quarks are never observed directly, but only used for a kind of bookkeeping of the families of particles, gives rise to an obvious question, which is, are quarks real fundamental particles, even though we don't see them directly? Or are they just an abstraction, a kind of a bookkeeping device? And there's a underlying question there, that's sort of a philosophy, which is like, what is the difference? If we can't see them in isolation, in what sense can we even really say that they're real physical particles versus a bookkeeping device? Like, what does that distinction mean in the case where there's no possibility to observe them experimentally? So the obvious question, having looked at this quark model that occurs to experimentalists, is, can I design an experiment to demonstrate that quarks are real? Is there some observable which would show me that there really is a substructure, for example, to the proton? Based on what we've seen so far, what kind of experiment could I do if I wanted to determine if the quarks are real? If I want to determine if the proton, for example, has an underlying substructure, what type of experiment might I try to perform? Any ideas? Devin, you want to take a shot?
Yeah, you could maybe try to do some kind of scattering to determine the internal components of the proton, whether or not they exist.
Yeah, exactly. So I think the inspiration here that we're thinking back to is the Rutherford experiment, right? At that time, people had ideas that maybe the atom was a sort of a plum pudding model with a diffuse positive charge with the electrons like embedded on the surface. And the way that Rutherford's experiment was able to distinguish this hypothesis from what we now know to be true, which is that there's a hard core at the center called the nucleus that contains all of the positive charges, is by firing some like high momentum probe into this mess and basically seeing how many large angle scattering events there are. If we're talking about a very diffuse distribution, whether we're talking about an atom or now the substructure of a proton, diffuse distributions, let's say that there was an even distribution of the electric charge inside the proton, then if I fire a probe particle, electrons are probably a good choice as a probe particle, since they're sort of easily available and easily manipulated by an accelerator. Then I should see only basically small angle scatters from that experiment. Whereas if there's some kind of massive point particles making up the proton, then I should see, relative to the expectation of the first case, I should see more large angle scattering events. So let me spend a couple of slides to go through a little bit of the formalism of how these scattering experiments are analyzed, and then we'll look at the results of the experiments and how they showed that there was a point-like constituent to the proton. So we start with this equation, which is the Rutherford scattering formula. So this would be the case where we can neglect any effects of the spin of the electron, and the electron is glancing off of a point-like particle. Alpha is the strength of the electromagnetic interaction. In a sort of Feynman diagram sense, what I should be picturing for this interaction is that the electron comes in and has a close approach to the target particle. It interacts with that target particle electromagnetically by exchanging a virtual photon with the target particle, and then that transfers some momentum to the electron, and it goes out at a different angle than it came in. This is a differential cross-section measurement here. So we're looking at the difference of the cross-section of the interaction as a function of the outgoing particle energy and angle. So we see that the cross-section, all else being equal, will be lower for higher energy particles, and the smaller the angle that I look at, the closer this side of the angle gets to zero, the larger the cross-section should be. E is the energy of the electron, and theta is the scattering angle. In this case, we're assuming that the particle that it's glancing off of is basically fixed. So you can imagine the target particle as sort of like nailed to the chalkboard, and therefore the energy of the outgoing electron has to be equal to the energy of the incoming electron in order for energy to be conserved. And that's why there's only one value of E here. But we can do better than this. The first thing that we can do is introduce the effects of spin and do the quantum mechanical calculation in the spinful case. And that modifies the formula a little bit. So we still have the factor of alpha squared related to the strength of the electromagnetic interaction. The denominator is still the same, but the effective spin introduces this cosine squared of 1/2 theta term in the numerator. So because this is in the numerator, the closer we are to 0 theta, the closer that this correction factor on the top is to 1. That is, for small angle scatters, there's relatively little effect of the spin. But as we get to larger and larger angles, this cos theta term, this correction increases. So it means that the effect of the spin on the trajectory of the particle is larger for large angle scatters than for small angle scatters. And otherwise it's the same. This is called the Mott cross-section formula. We can further make this equation more realistic by releasing the assumption that the target is fixed. So in the case of like a low energy electron glancing off of a nuclear target in the Rutherford experiment, the assumption that the target nucleus is fixed, you know, picturing like a metal where this gold atom or whatever is basically not moving around too much inside of the metal. That's going to be less true as we move in these experiments to higher energies, where the mass of the particle that's being probed is also going to play a role in the kinematics. So we can define what happens in the case where the target particle is actually not fixed and instead undergoes a recoil when the probed particle bounces off of it. Then E prime is the outgoing electron energy, and that's related to the initial energy by this correction factor here in the denominator. which depends on the energy of the incoming particle as well as the mass of the target. So this is very similar. It's basically the relativistic version of, bouncing ping pong balls off of bowling balls or whatever. The closer in mass the particle becomes to the energy of the electron that's coming in, the larger this correction factor down here will become, which I think makes sense. In that recoiling case, it's useful to define a quantity which we're going to call Q squared, which is the square of the momentum transfer between the probe particle and the target particle. So this Q squared, if you do the relativistic kinematics, is going to come out to -4 times the product of the incoming and outgoing energies times this factor related to the angle of the scatter. So again, the larger the scattering angle, the larger this sine squared theta becomes, and the larger the momentum transfer is. And we can actually write down the full expression for the elastic scatter of an electron from a point like Dirac particle, and that's this equation down here. So the first part is remaining the same as we had on the previous slide. But then we have this additional factor, which it's multiplied by, that includes the ratio of the incoming, the ratio of the outgoing to the incoming particle energy. And then this correction factor here, which has to do with the scale of the momentum transfer and the mass of the probe particle, as well as this tan squared of the angle. Note that as the mass of the particle, the target particle, gets large, this correction factor is going to get small. And because of kinematics, this E prime therefore will approach E. And this whole thing basically becomes 1. And we recover the Mott formula from the previous slide as expected. So this correction for the elastic scattering of an electron from a point like Dirac particle reduces to the Mott formula in the limit where the target particle gets very heavy. Well, all of the results on the previous couple of slides are all for the case of a point like target. But as we said, the whole idea that we're trying to test in these experiments is the hypothesis that the target is actually not point-like, but rather has some kind of spatial extent, and maybe even there's individual particles or something bound up in there. So what we would like to do is define a function which describes the spatial extent of the charge in the target. And this is a so-called form factor. I guess that's why they use capital F, F for form factor. And this form factor is a function of the momentum transfer. And it basically describes the interaction of a point-like particle with a spatial charge density, which is a function of the location in space. That's this rho of R. So people are refining the art of doing these differential cross-section calculations for various scenarios. So I described on the previous slide adding in a form factor which covers the case where the charge of the target particle is distributed in space. There are then further refinements made here, people doing quantum field theory calculations to account for not only the spatial extent of the proton's charge, which gets absorbed into this form factor F1, but then also the effect of the proton's magnetic moment. So the electron can interact with both the charge distribution of the proton, but also with its can also interact with it magnetically. And so you end up with these increasingly complex scattering amplitude formulae that account for both of these effects. And you can see that there's some dependence on this number kappa, which is new. Kappa is the anomalous magnetic moment. In the case of proton scattering experiments, that would be of the proton. People will eventually do these experiments also on neutrons, where F1 is 0, has no net electric charge, but F2 is still non-zero. The neutron also has an anomalous magnetic moment, just with a different value of kappa. And then you have a second part of the expression here, which also depends on these, both the charge form factor F1 and the magnetic form factor F2. So this is a sort of state-of-the-art calculation in, let's say, the mid-1950s of what we would expect the scattering cross-section for electrons from a proton to be if the proton has some spatial extent, but no substructure. So basically, you imagine that the spatial extent of the charge distribution and the magnetic moment are allowed to be different, but there's no allocation in this formula for the idea of point-like constituents. So this is the prediction in the case where the proton has a smooth, continuous density in a limited region of space. So then the obvious next step is to go and make an experiment which measures this this differential cross-section precisely, and even then you can attempt to derive what these form factors for the magnetic moment and the charge actually are based on the cross-section, differential cross-section that you measure. This experiment is done. There's a series of experiments starting in the early 50s and concluding by 1956 with this paper, which is called Elastic Scattering of 188 MeV electrons from the proton and the alpha particle. So in the late 50s, the technology for building a linear electron accelerator, which we'll talk a bit more about in a few slides, is starting to be under development. So they're starting to assemble this accelerator complex at what will eventually become SLAC, the Stanford Linear Accelerator Center at Stanford. Here it's still just called High Energy Physics Laboratory of Stanford University. So the idea here is the following. We are going to use hydrogen as our target. This is a convenient target to use for these types of experiments because hydrogen has a very simple nucleus, which is just one proton. So we don't need to worry in this case about any contribution from neutrons, which will have a different F1 and F2 as we just stated on the previous slide. So you have a pressurized vessel with thin walls, 10 mils of stainless steel. So that's 10 thousandths of an inch of stainless steel is strong enough to hold some amount of hydrogen gas under pressure in this vessel. And then you place this vessel into the electron beam at the Stanford accelerator, and you allow electrons in the beam to scatter off of the protons in this hydrogen target. And then you basically have a monitor at one end, which is measuring the amount of current which passes through the target. This is useful for normalizing the measurements to the total amount of beam current. And then you have a spectrometer, which consists of an analyzing magnet and then some counters, so that you can set the magnetic field such that electrons of one specific momentum will fire the counter. And then you put this whole thing on a moving table that allows you to rotate it around the target. So at each sort of stop of this spectrometer, you choose the angle that you're going to measure. Maybe I want to sit here at 90 degrees. So I move my spectrometer there. And then I can ramp up the current in the magnet of the spectrometer step by step and observe how many counts I get per unit time as a function of the current in the spectrometer. So this will enable us to measure both the scattering angle theta and the outgoing electron energy E prime. And those were the two observables that we needed in order to be able to do the differential cross section of the Rosenbluth formula on the previous slide. I won't discuss it any further here, but they did also have the idea to put in a target which did contain some neutrons. So they could also fill this vessel with helium gas. So there you have nuclei, which are alpha particles consisting of 2 protons and 2 neutrons. And they also measured the differential cross section for that, which gives some information about the difference in the form factors for protons versus neutrons. But as I said, we won't really discuss that too much further. It starts to sort of go into the realm of more nuclear physics. Here are some results. So on the left hand here, you have the energy of the scattered electron as the y-axis of this plot, and then the laboratory angle, that is the position of your spectrometer as the x-axis here. And so for each of these angles that they move to, they would then scan the magnetic field of the analyzing magnet in the spectrometer to find the value for which the count rate is maximized. And that's what you see plotted here. The prediction of the Rosenbluth formula is the solid line here. And you can see that although the match is not 100% perfect, it does a very good job, especially qualitatively, of predicting most of these points. Arguably, there's some fall off visible in the first point here and in the last few points here. But it generally confirms the picture that the Rosenbluth formula, which assumes some kind of spatial extent to the proton, but no point-like constituents, is sort of a good approximation, at least at this energy of 187 MeV. It's a little more interesting when they sort of measure the cross-section itself as a function of the scattering angle. So this is the energy for which you observe scatterings of that angle, but you can also calculate the actual cross-section as the number of events that you should observe. And there seems to be a departure from theory. So this figure 5 is from the same paper, and it shows the Mott prediction, which we had, I guess, 3 slides ago, as a dashed line here. The Dirac curve here, which is the Rosenbluth formula. And then C is what you would expect to obtain if the proton itself was truly a point charge, both in terms of its electric charge and also its magnetic moment coming from a point particle. And what we see is that the observed curve falls somewhere in between the Rosenbluth formula and the point assumption. And they give the following interpretation in the paper. They say this deviation from the theoretical curves represents the effect of a form factor for the proton and indicates structure within the proton, or alternatively, a breakdown of the Coulomb law. So this could also occur if for some reason the strength of the electromagnetic interaction at these small distances, distances of like 1 Fermi, were to be different than what the Coulomb law predicts. And then they also extract from here an estimate of the size of the proton, which is about 7 times 10 to the minus 14 centimeters. So this is very interesting. It's you know, they've hit basically on the correct explanation in their interpretation here. Indicates structure within the proton, which is not totally unexpected, since people are investigating the possibility on the theory side that there might be some substructure like this Quark model, although this is still fairly early in the game. This is 1956. However, this evidence is pretty indirect. I mean, you can see that the error bars on these points are sort of similar in size to the departure from the various curves, although this is a log plot, so be careful there. But what you would really like to do would be to somehow expand this part of the plot where the difference between the different hypotheses is maximal, and repeat the experiment to try to get a conclusive demonstration if what we're seeing is due to some substructure, due to some breakdown in the Coulomb force at small distances, or to something else. And that desire to do that is going to correspond to the opening of a new energy range at SLAC in the 1960s with the opening of their new 18 GeV electron line. So remember the experiments that we saw on the previous slides, which suggested that the proton might have some substructure. That was done all at an energy of 187 or 188 MeV. Now we're talking about leaping up to 18 GeV. So this is almost a factor 100 higher in energy. So you can see this is an aerial photograph of the accelerator complex at SLAC. It's prominently visible in the foreground here, this long, straight surface building, which houses the linear electron accelerator at SLAC. If I am in the business of building a high energy electron accelerator, why would I do it as a linear accelerator? What's the reason for, a linear accelerator comes with some downsides, most notably that I cannot reuse my accelerating element the same way that I can in a circular accelerator, right? I have to do everything, all the acceleration in one shot. It's pretty expensive to engineer because if I want to make this accelerator more energetic, given fixed electric fields inside the accelerator, the only way that I can do that is to make the building longer. And so to build a building which is like 3 miles long, which is how big this SLAC accelerator complex eventually was, that's obviously a big engineering expense. So what is the reason why I would prefer to have a linear accelerator if I'm in the business of making very high energy electrons?
Electrons will radiate a lot of energy away if you try to put them in a circular collider.
Exactly right. So if I was building a circular storage ring for 18 GeV electrons, I can do it. People have built storage rings of even higher energy. However, I'm going to lose a ton of energy to Bremsstrahlung on each pass around the accelerator, because every time my charged particle moves, it's going to radiate energy, and that amplitude of that radiation is going to be proportional to 1 over the cube, or sorry, 1 over the 4th power of the particle mass. So relative to protons, which are a very good candidate for acceleration in a cyclotron, this situation where I'm trying to accelerate electrons much more favors the linear geometry. The basic idea of the linear accelerator is not that different from the other accelerators that we talked about. My goal is to produce electric fields in the spaces between these accelerating elements. So I have basically circular metal shields around the beam pipe, and then these shields are connected to a sinusoidally varying voltage source. And the goal is to match the length of these elements to the expected energy of the electron, such that as an electron leaves, for example, C1 and going into C2, it does so just at the moment that the electric field between C1 and C2 is pointing, it has its maximum amplitude pointing along the direction from C1 to C2. And then by the time I get to C3, we've gone through one half cycle of the voltage source, and now the electric field is pointing from C2 to C3. So by varying the frequency of the voltage that I apply to this arrangement, and by varying the length of these individual detector elements in order to have the proper combination of values such that my accelerating field is going to reach its maximum just at the moment that the electrons get here. Another reason that this linear geometry is nice for electrons is that, in this cartoon, it's rather exaggerated, the difference in length, for example, between C1 and C4. Obviously, as the particles get faster, we need to lengthen the distance between our accelerating elements so that they're still arriving in time at the moment when the electric field is pointing in the right direction and has the right amplitude to do the acceleration. But practically speaking, since electrons are so light relative to the energies that we're talking about, they almost immediately get so close to the speed of light that this difference in distance is not really significant. So if you were to walk along this long hallway, the accelerator itself is underground, but the voltage generators are on the surface, more about which on the next slide. But the actual distance between the accelerating elements is fixed to a very high degree of accuracy, because almost as soon as the electrons pass through the first few elements, they're so close to the speed of light that the difference in the travel time through the successive elements is not significant. And that simplifies a lot the engineering of the machine. If you had to greatly change the spacing of the elements as you went along this thing, you would be sort of locked into one really specific energy. But the fact that the electrons so quickly attain the relativistic limit means that you can sort of reuse the same size detector or same size accelerating elements along the beamline, which reduces a lot the engineering cost and complexity. Main technical challenge is actually generating the radio frequency waves to do the acceleration. Remember that in the circular accelerators, we can reuse one RF cavity and just change the frequency as the energy of the particles in the ring increases, right? We ramp up the current in the steering magnets to keep them traveling in the same radius, and then they just pass through the same RF cavity over and over again and get a kick each time. In the LHC, for example, there's one location around the ring where the acceleration is actually applied, and the rest of it is just bending magnets and beam optics to get the particles back to that location. In this linear geometry, we can't take advantage of that, and so we have to place a relatively much higher importance on having a powerful and reasonably energy efficient acceleration technology to make these radio frequency waves that are necessary to do the acceleration. And that's done by means of a technology called the klystron. So klystrons are a general purpose technology that are used in all kinds of devices that want to generate sort of microwave frequency waves, but they're especially important to particle accelerators. There's sort of a schematic view of how a klystron works on the lower left of the slide here. This illustrates a two-cavity klystron. In the real world, klystrons can have more than two cavities, but the principle of operation is more or less the same. So what is a klystron? You have two cavities or more, and cavities are either catchers or bunchers. So you input a weak microwave signal, and this thing basically acts as a microwave frequency amplifier. Generating microwaves is not so straightforward. So you need to have some kind of clever design in order to do it with a good power efficiency, and that's what the klystron does. So you apply the signal to be amplified to the buncher cavity, for example, through a coaxial cable or through a waveguide, and then you can extract an amplified microwave signal from the catcher cavity. And in this case, for a linear accelerator, that microwave is then passed through a waveguide going to the actual volume in which the electrons are to be accelerated. So at one end of the tube, you have the electron source, or the cathode, which is producing electrons that are flying off the cathode into free space, for example, by means of heating a filament. The electrons are then pulled forward by this anode here. So you have some accelerating voltage that pulls electrons off the cathode and sends them flying through. So the cathode and anode working together basically are an electron gun, which is going to produce a stream of electrons to be amplified. And then you have external magnetic field, electromagnet winding around this region that produces a longitudinal magnetic field. What would be the purpose of applying a longitudinal magnetic field to the electrons? What is the longitudinal magnetic field going to do for my beam of electrons? Will a longitudinal magnetic field apply any force to electrons which are traveling along the direction of the field lines? And the answer is no, right? Electrons feel a force if they travel with a velocity perpendicular to magnetic field lines, but they don't feel any force from longitudinal magnetic field lines. So basically this acts as a direction selector. It will amplify electrons which are traveling precisely along the direction of the field lines, and it will basically screen out electrons which have any momentum perpendicular to that direction. So it basically focuses the beam, or at least screens out electrons which aren't traveling perfectly in line. So then this beam passes through the first cavity, the buncher, and the buncher has oscillating potential across it. So imagine that there's two electrodes at the sides of this cavity, and the electrons are passing through, and as they pass through, they're exposed to this oscillating AC potential. So this potential is arranged to have standing oscillations inside the cavity. And it's, excited by this input frequency here. And the direction of the field between the two sides of the buncher cavity is changing twice per cycle of the input signal. So electrons are going to enter when the entrance side is negative and the exit side is positive. So that will produce an electric field in the same direction as the motion of the electrons. Basically, they get accelerated by the field. Electrons which would enter out of phase with this oscillating voltage will have the opposite condition, where they're going to feel a force retarding their motion. And so they'll basically get slowed down, and they'll wait inside the cavity for the next time when the AC signal is pointing in the right direction. And what you have then coming out of this buncher cavity are pulses of electrons, which are in time with the input signal here. Then you have a drift space. And this space is chosen to be long enough that the accelerated electrons will catch up with any electrons that were decelerated from the previous cycle. And so this drift area, basically bunches of electrons emerge naturally because of the different velocities that were given by the buncher cavity. And then you pass through the second cavity called the catcher, which has basically the same design as the buncher. But the catcher basically then absorbs the energy from the electron beam. So the bunches of electrons passing through here basically create standing waves in the cavity. This cavity is designed to have the same resonant frequency as the buncher cavity. And it will then absorb the energy from decelerating the electrons, and that produces an amplified output signal here. So this kind of infographic from Slack describes this action as being similar to an organ pipe. And that analogy does kind of make sense, in the sense that if my vibrations in the organ pipe are the right frequency to match the physical extent, then they'll be amplified, and any vibrations which are the wrong wavelength for the cavity will be suppressed. The same is true in this klystron. So by choosing the input signal, you can basically use these electrons to deliver power to the catcher cavity in a bunched way, producing output signal of the same frequency, but with a greater power. And then this sort of depleted electron beam, which has been mostly decelerated, then falls onto a collector electrode here, and the circuit can return the current back to the beginning. So this whole thing is a way of amplifying microwaves coherently, such that you can then inject them into the cavity of the accelerator and do the acceleration of the electrons in the beam pipe. So this new 18 GeV beam at Stanford is used to do experiments which become known as deep inelastic scattering experiments. So in the previous experiment, the one which was done with the 187 MeV electron beam, what we mostly saw was elastic scattering. We saw that the difference between the predictions for point-like particle with some form factor, which is continuous, the reality falls somewhere in between, suggesting that there may be multiple point particles inside of the proton. But all of that is just looking at the momentum of the outgoing electrons. Once we get to very high energies, for example, the 18 GeV, which this new accelerator at Stanford can produce, then we open up the possibility that the interaction between the electron beam and the proton target can be inelastic. So the electron isn't simply scattering off and going off at a new angle, but we actually produce new particles. You can have a recoiling, sort of the hadronic debris of the proton. The proton is broken up in these interactions, and you have other particles, mostly pions, coming out. The invariant mass of that system we call W. And then we have the outgoing electron, and there's a momentum transfer Q, which is the difference between the incoming lepton momentum and the outgoing lepton momentum. And some of this Q can go into just steering the electron, but some of it can also go into producing this hadronic recoil. We define a new variable for these inelastic scattering events called W1 and W2. These are each functions of a variable that we call nu, which is the energy lost by the electron in this interaction in the lab frame, and q squared, which is the square of the momentum transfer. So in the inelastic case, where we don't form any new particles, these two things, the energy lost by the electron and the momentum transfer, are 100% correlated. But once we open up the possibility to produce new massive particles in the interaction, that correlation is lost. And so we need these new functions, W1 and W2. W1 is absorbing a part which is proportional to the tangent of the scattering angle, and W2 is basically a constant contribution to the overall cross-section. So the nu and the q squared are no longer exactly correlated in the inelastic case, and we have to instead determine W1 and W2 from data. And the way that we do that is by measuring the differential cross-section at different values of E prime or K prime and theta that correspond to the same values of nu and q squared. So you can go to a different angle, for example, and then find the population of electrons which lose the same amount of energy as your previous point, but in this new direction. And by making a bunch of comparisons of that type, you're able to extract the values of these functions W1 and W2. A guy named Bjorken, who's working from the assumption that the proton is actually composed of point-like constituents, predicted that what we should see in experiments of this type is a hard component of the cross-section, which doesn't fall off rapidly at high q squared. So in general, in the elastic scattering, the more momentum transfer that we ask for, the lower the cross-section is going to be. But if there's true that there's point particles inside the proton, there should be some kinematic range where this fall off is suppressed. And that's because we're no longer interacting with the proton as a whole, but with these individual point particles inside of it. So the main experimental challenge here is to discriminate, actually, are you measuring an electron from the scatter, or are you measuring pions, which are part of this hadronic recoil? So we want to measure K prime in the language of the previous slides, not the number of events of W. So the main challenge is to discriminate those recoiling electrons from pions, which are produced in the inelastic events. So we have an electron beam coming in. This is in spirit very similar to the previous experiment that we looked at, but the detector is a little more complex. We have some magnets along the beam direction, which are to enforce that the beam is really monochromatic, reduces the spread of the beam. You're selecting a particular direction and momentum that will pass through those magnets along the beam line. The target, again, is hydrogen gas for the same reason. You have this Faraday cup, which is placed either in the axis of the beam or just off of it. Faraday cup is basically just a winding of wire that when the beam passes through, it induces a current. You can measure that current, which is proportional to the current in the beam, which is inducing it. At low intensities, you can put this thing directly in the beam. At higher intensities, it would burn up, but you can put it off axis of the beam and measure sort of the edge of the Gaussian profile of the beam and control the intensity of the beam that way. And then you have some counters, which are measuring the flux of particles coming through along this spectrometer arm. You have a Cherenkov counter, which is an electronic counter, which is going to fire whenever highly relativistic particles pass through. You have what's called a hodoscope, which I will define on the next slide. And finally, you have a pi-e discriminator, which solves your main experimental challenge. So we want to tell pions apart from the electrons. There's different ways you could do that. If you were restricted to a single momentum range, you could think about building a Cherenkov particle ID system in here of the type that we described in the last lecture. But this experiment actually uses slightly different principle. The pi-e discriminator is basically a 3-layer, what we would call now sampling calorimeter, 3 layers of lead interleaved with 3 layers of plastic scintillator. And the insight there is that electron showers are typically much shorter in lead than pion showers for reasons that we'll return to in the next couple of lectures. But basically use the longitudinal profile of the shower, like the ratio of events firing the third station to the ratio of events firing the first station. You make comparisons like that, and you're able to efficiently discriminate electrons from pions. We'll discuss the microscopic nature of hadron showers a little bit later on. This is a picture of one of the hodoscopes that they use. It's one of the first kinds of really tracking detectors, which can be read out electronically. The idea here is quite simple in principle. You have scintillating plastic, which is drawn into long fibers. And each of those fibers has its own waveguide going to eventually a photomultiplier tube. And so you can basically reconstruct particle trajectories just by knowing like which of these scintillating fibers was fired by a particle going through it. If you like, then you can put a second plane behind this one and rotate everything 90 degrees. Then you have like an X readout from the first plane, a Y readout from the second plane, and you can reconstruct what the like 2-dimensional trajectory of the particle was. And sometimes in long complex beamlines, you might have many hodoscope stations along the way, which are not just providing indication of whether a particle passed through or not, but also where the spatial location of the particle was. And these kinds of tracking detectors are soon to reach much higher levels of sophistication that we'll talk about in the next lecture. Anyway, here's the results of these deep inelastic scattering experiments done with the 18 GeV electron beam, and the results are quite striking. Here you have the prediction in a dashed line of what you would get in the elastic scattering only case. This is parameterized as the cross-section that you observed as a ratio to the cross-section predicted by the Mott formula from a few slides ago. And then you can draw this cross-section as a function of the momentum transfer squared, Q squared, down here. So in the elastic scattering case, what you would expect is a smoothly falling distribution. Basically, the more momentum transfer that you're asking for there to be, the less frequent it should be, and therefore the lower the cross-section relative to the simple Mott formula. But what you actually see is quite different. By looking at different amounts of hadronic recoil, you can see that there's essentially like a flat component here that like no matter how much Q squared you ask for, the cross section is not only much higher than the Mott prediction, but also doesn't vary much as a function of the momentum transfer. So this is just qualitatively very different than what you would expect for the case where you have just a single continuous underlying distribution. And it is strongly suggestive that the proton has individual point particles inside, much more clear and much more striking than the signal that we saw from the 187 MeV measurements back on slide 18. This is called Bjorken scaling. Basically, the way that this cross-section scales with the energy in this flat way rather than the sharply falling way that we would expect in the elastic case. It's known as Bjorken scaling, and it is considered to be a smoking gun for the case that protons are not fundamental. They do have substructure, and even though we can't remove a quark from the proton to study it in isolation in the lab, we can actually reveal that they are real objects through their effect that they have on the scattering cross-section. There's an effect which is consistent with point-like constituents and not with an even distribution of charge and magnetic moment inside the proton. So Feynman looked at these data and came up with a model called partons, which is not exactly the same as our current understanding of how the quarks make up the proton, but it has some of the essential features, and it's pretty easy to understand his argument. So Feynman starts out his paper saying that, of the total cross-section for very high energy electron-hadron collisions, perhaps, a small fraction, as we saw in the previous slide, can be explained by the elastic part. And most of what we see at these higher energies is really down to the inelastic part. It's a hard thing to analyze. You may wonder, why did we define all these weird quantities like Q squared and nu and W and all this stuff? And the answer is that the events are becoming so, there's multiple particles produced in one of these scattering events. There's a couple of different kinematic quantities of the electron. Then there's the invariant mass of all the hadrons, their individual directions, the number of hadrons that's produced. It's hard to parameterize things in a way that makes it obvious what's going on. And so this parton model is really an attempt to paint a physical picture that should aid in the interpretation of the experiments. So Feynman's model is that the proton is composed of point-like constituents, which he calls the partons. They're obviously identified with the quarks that Gell-Mann proposed, but Gell-Mann's theory didn't really make quantitative predictions about what the outcome of these deep inelastic scattering experiments should be. So Feynman's model kind of stitches together a kinematic understanding of what's happening in deep inelastic scattering with the underlying idea that these partons are the quarks. His idea is that they share the momentum of the proton by taking each a variable fraction, f of x, where x is the fraction of the momentum, and then this f of x is how often an individual parton has that much momentum, has that fraction of the momentum of the total proton. And the key insight here is that this fraction is not a property of the specific interaction being studied, but is instead an intrinsic feature of the proton itself for a given momentum. And that will become important on the next couple of slides. As I said, the partons are naturally identified as being quarks. So this extends the scheme that was suggested by Gell-Mann and others, but Gell-Mann's eightfold way and all that stuff was really just talking about what today we would call the valence quarks. Those are the quarks that make the main contributions to the observable quantum numbers of the particle. But Feynman had the insight that there can be an unlimited number of virtual quark anti-quark pairs inside of the proton, which carry some of the momentum, even though the fact that they're paired up quark anti-quark means that they don't have any real effect on the quantum numbers of the proton. That's not exactly true, but it's a good approximation, especially at the energies that they were talking about. And this is the first idea of this difference between what we now call the valence quarks and a sea of quarks and gluons, which make it up. Feynman had no conception of gluons at this point. And so his model doesn't make really good quantitative predictions, especially as we get to higher energy where the gluons become increasingly important. But it does give the right mental picture of what's happening inside the proton, which is that there's not only these 3-point-like particles, which are sort of bound together, but there's also a sort of stew of stuff in there, which is helping to do the binding. And then the scaling behavior that we see in the deep inelastic scattering experiments is sort of naturally explained as the electrons are sometimes hitting the parton. So the sort of inelastic part that you see where they're just smoothly deflected, that's when they're kind of plowing through this C. But occasionally, just like in Rutherford's experiment, you hit the hard core and you get one of these big scatters. And the fact that that doesn't scale in the same way with the momentum transfer as the inelastic part is the smoking gun that these partons have a real underlying reality to them and are not just a bookkeeping device. Here's how we would draw these parton distribution functions today. So you can see that there's components for the valence quarks, which are these things that are peaking at higher values of X. So typically a valence quark at this energy mu squared of 10 GeV, that's like Q squared of 10 GeV. The valence quarks are maybe carrying an X of 0.1, something like that, whereas these C quarks are carrying, 1/1000th or 1/10,000th as much of the momentum. The parton distribution function does change depending on the momentum transfer that we image it at. So if we increase by a lot the momentum transfer, here we go from a mu squared of 10 GeV up to a mu squared of 10,000 GeV, or 10, 1,000 times higher in the square of the momentum transfer. We see that the fraction carried by these C quarks, the X times f of X for these C quarks and gluons, increases by a lot. And then even this gluon line here is divided by a factor of 10 just to partially fit onto the plot, but it already overruns the scale at 10 to the minus 2. So this is important if you're analyzing, for example, something like Higgs production at the LHC, where the momentum transfers involved are very large. You essentially enter the regime where it's the gluons which are doing most of the work, whereas in lower energy scattering, the valence quarks are playing much more of a role. And I think that kind of intuitively makes sense if you think of the physical picture that Feynman was sketching. Since these are properties of the proton and not of the scattering experiment, we should also be able to scatter other particles off of the proton and observe these same PDFs. And people start doing that with neutrinos, in part motivated by concurrent developments in the electroweak theory. So I'll say just a few words about that. So the electroweak theory, Fermi wrote down his theory in the 40s to explain weak interactions. He was mostly concerned about like beta decay, trying to explain where the momentum goes that's not visible in the recoiling electron from a beta decay. He hypothesizes that there's this neutrino, which is weakly coupled to the electron, and that's how you end up with these decays that have a long time scale attached to them because the interaction is so weak. And he was only interested in the charged current interactions. There was no idea, for example, of looking at neutrino exchange. And people actually, by this point in like the 1960s, had experimental upper limits on the amplitude of flavor changing neutral currents or currents which in our modern understanding we would say are carried by the Z boson rather than the W. You can extract those, for example, by looking at the rate of different strange decays and seeing if there are decays which are mediated instead by the neutral current. So a neutral current event would look something like this. You have a beam of muon neutrinos, for example, going into your target. They scatter off the target by exchanging a Z boson with it. And since the Z boson isn't going to change the charge or flavor of this electron, the signature would just be, you shoot a beam of neutrinos onto the target, and once in a while, you should see a recoiling electron come out. That would be the smoking gun for weak neutral currents. And this is sort of concurrent with developments in the idea of electroweak symmetry breaking, which again, we'll talk more about later. But there's a prediction already by the late 60s that there should be these weak neutral currents and even a prediction of the amplitude. There should be two types of neutral current events from a neutrino beam onto a hadronic target. One like we see here, which would be the leptonic case, and then another which would involve exchanging Z with some quark inside of the proton, and then you can have like a shower of hadrons coming out. So as progress is made on the theory side, there's interest in doing these deep inelastic scattering experiments with neutrino beams on targets of hadronic matter, not just to verify this like weak theory, but also to confirm the quark picture that we really do see the same underlying parton distribution functions using a beam of a different type, right? That's one of the cornerstones of Feynman's parton theory, that this thing is these X functions are a property of the proton and not of like the interaction between the proton and the probe particle. So people build, I apologize for the extremely low resolution of this diagram. What it is supposed to show here is the method by which neutrino beams are produced in accelerators. The basic idea is quite simple, and we talked about it already with the BNL neutrino beam in the previous lecture. The idea is basically just to shoot protons onto a target, then have a bunch of absorber, so anything besides neutrinos gets soaked up. And then you just, whatever neutrinos emerge from decays in flight in that decay region can then pass through your experiments. This is a picture of the target. This is an experiment at CERN using this massive bubble chamber called Gargamel. This picture was taken in, I guess, the early 70s, maybe 1972. This bubble chamber is huge. It's 2 meters in diameter and 4.8 meters long. The beam is going to be entering, I guess, from along this axis to give the decay products, which are picking up momentum along this direction, time to interact and be photographed. And there's a neutrino beam of about 2 GeV of energy entering this thing. And then the goal is to look for these both charged and neutral current events. Simultaneously, Carlo Rubbia and collaborators have an analogous experiment that they set up at Fermilab using electronic detectors rather than bubble chambers. Remember, one of the main drawbacks of the bubble chamber is that you have to expand the chamber before the interaction happens in order to get the bubbles. And therefore, in a case like this, where you're studying very rare events, you might have to shoot, tens or hundreds of thousands of pictures of film just to zoom in on a few rare events, because you don't have any kind of triggering system. You had to expand before you knew what happened or not. This experiment, which was called E1A at Fermilab, this is a 10 GeV neutrino beam, and instead of using bubble chambers, they're using spark chambers interleaved with absorbers. So very similar in spirit to the Brookhaven neutrino experiment we talked about last time that verified the existence of the muon neutrino. And then using the spark chambers, you can actually image particle trajectories coming through this mass of absorber and look for both the leptonic events where you would just see like one track going through, and contrast that with hadronic events where you see a kind of shower due to the hadrons that are produced in the deep inelastic scatter. So there's sort of a schematic view of this experiment shown here, that like you have a muon spectrometer behind what we would today call a calorimeter. The calorimeter is good at making images of the hadrons that are produced in a hadronic scattering event, and then only muons will penetrate to this muon spectrometer behind. These experiments were hard in part because the idea of a quantitative background prediction from like Monte Carlo simulation is just starting to be a thing. So we're talking about the 1970s here. Computers are finally getting powerful enough that we can do Monte Carlo simulation to try to estimate the rate of like rare classes of background events. But the whole field is still in its infancy. So typically these Monte Carlo simulations are giving sort of order of magnitude type estimates. And it's actually, as a result, very hard for these experiments to say whether they really observed anything or not, since there's not a huge amount of information in these spark chambers relative to what you could see from a bubble chamber, where you can look at successive generations of the interaction and things like the specific ionization along the tracks. This is a good idea. It's a simple type of experiment based on electronic counters. It looks like the future, but they weren't quite ready for the future yet because they couldn't estimate with a high degree of confidence what the background they would see is. So as a result, this is one of the last discoveries in physics, which is still made by means of a bubble chamber. These are the pictures from Gargamel, who claimed the discovery of the neutral currents in 1973. You see at the top here a hadronic event without a muon. So there's 3 high momentum hadrons coming out of this deep inelastic scatter of a neutrino off of a nucleus. And then each of them have their own little lives as they go through the bubble chamber. On the bottom, you see the leptonic event, which is much cleaner. You just have like a single electron, which comes basically out of nowhere. So the idea is that a neutrino is traveling through, it exchanges a Z with an electron in the material, and then this electron goes through, a few times it loses a big fraction of its energy to single Brem events. Then you can see the E plus E minus pair, which comes out. That happens again here. But these pictures are considered to be a smoking gun that the interactions of the neutrinos with matter, the cross sections that are extracted from these experiments are consistent with the Proton models, consistent with the idea that the underlying structure of the hadrons is the same, whether I'm using a charged lepton or a neutrino as my probe particle. This is also a dramatic confirmation of the electroweak theory, and opens the possibility that we might be able to build an experiment to directly detect the W and Z bosons themselves rather than the interactions that they mediate. And we'll return to that topic later on in the course. So as I like to do in each of these lectures, here's what I think the standard model would have looked like to someone in 1973 or 1974. The electrons and muons are point particles. Baryons and mesons are made up of component fermions called quarks that carry different quantum numbers and also have some relation to the masses of the particle. The quarks come in 3 flavors: up, down, and strange. This SU3 symmetry that inspired the eightfold way suggests that there might be 3 color charges that these quarks can have. So color is hypothesized to be the charge of the strong force, and hadrons have no color charge, either because they are formed of a quark-anti-quark pair of opposite color, or they have 3 component quarks in the case of baryons, each with their own color charge, which cancel out. The quark model is successfully used to predict the existence and even estimate the masses of new hadrons. For example, the omega minus with strangeness of -3 was a strong piece of evidence in favor of Gell-Mann's quark theory. And the weak interactions are allowed to change strangeness by 1 unit. That's the reason that the strange particles decay slowly, because they have to decay through this weak force in order to shed the units of strangeness that they have. And another topic which we'll come back to is the idea that the weak interaction also seems to be strange in terms of the way it treats the symmetry of nature called parity. By this time, people have evidence from experiments with nuclei and with the neutral kaon system that parity is not conserved in weak decays. But there's much more to say about studies of the weak interaction and of the electroweak theory, and that will follow in succeeding lectures. So I'll stop here for today. We have a couple of minutes if there are questions. I don't see any. I will be posting the second problem set on the course webpage soon. I know I've also been delinquent in posting the recording of the previous lecture, so I'll do that along with the recording for today's lecture. I'll try to get, for those of you that are taking the course for credit, I've been a little bit slow in grading that first problem set, but I'll get to work on that. soon, and I hope to have those back to you sufficiently in advance of the second problem set being due, that you can make use of the feedback that you received. But I think that's it for today, and I will see you guys next week, where we will continue on to the age of particle colliders and start to get much closer to what experiments that look like what we do today. Bye.
See ya.
Bye, thanks.
Thanks.